Welcome back, everyone. Hopefully your spring or your fall break was enjoyable. I'm getting over a little bit of a rot here. I was sick over break, so hopefully my voice lasts. Find out. Today we're going to finish up nomenclature. A couple of key things I want to point out about that in terms of the rules. We'll go through some cyclic compounds real quick, and then we'll go into conformational analysis. So we'll look at a little model, and really that is talking about a single molecule that, when it undergoes rotations, forms conformational isomers called conformers. So the reason that's important is because that will ultimately help us, again, predict reactivity. Because the way we draw things is not necessarily the way they react, and we need to use these models to help us determine that. Any questions before we get started? Okay, so seeing none, we'll review that question we left off on because it was kind of rushed. What is the name of this molecule? These nomenclature problems for alkanes are, quite frankly, pretty boring, but they do illustrate the rules of nomenclature. There are some subtleties, which I'll just skip to the next slide that shows the answer, and show you what you really have to look out for when you're finding the longest chain and then numbering it either way, because that's really going to help you determine what way you should number it and then how you identify the substituents. So the correct answer for this was A, 6-ethyl 3,5-dimethyl 4-propyl nonane. Let me just point out a couple things about the name first, and then we'll look at why B is wrong and why C and D are definitely wrong. So the first rule of nomenclature is you need to find the longest carbon chain. So that determines the parent name. And regardless of the functional groups that are present, the parent is always derived from an alkane. So that's why you need to know methane through decane by heart, basically. So if we trace along this in green, as you see, that's the correct longest chain. For choice B, that's also a 9 carbon chain, but it's highlighted in yellow, so that's not the best answer. So let me point out some key things about the correct answer. Anything bonded to the longest chain is called a substituent. You name the substituents according to the number of carbons in them. So you take the alkane name, you subtract off A and E, you add YL, and that gets you the substituent alkyl. The nomenclature rules state that substituents are listed in alphabetical order. So if you look, we have E, M, and P. So alphabetical order. Notice the numbers associated with those substituents. The number is called a locant, or the location where the substituent occurs. The substituents, as I said, as I emphasized, are in alphabetical order, not the order of those numbers. So those numbers are what they are. the substituents go in alphabetical. You separate a substituent from its locant with a hyphen. And then if you have two of the same substituents, so let's methyl, there's two of them, you have to specify their locations with numbers, and then you separate those numbers with a comma. Since there's two of them, you have to use these other prefixes. So like di, tri, 4 is called tetra. So let me just write those down here. So same substituent. So it's probably rare that you get above 5, but that's what you would need to use to identify multiple of the same substituent. So 6-ethyl 3,5-dimethyl 4-propyl nonane. And the key to all of this, the reason why A is correct and B is not, is once you find the longest chain, what that does is minimizes the chain lengths of the substituents bonded to that. So what I mean by that is choice B here with the chain outlined in yellow. See this substituent here, 2-butyl? That's at position 6. So that group is at position 6. The 2 means of the 4-carbon chain, it's bonded at position 2 on that 4-carbon unit. The reason that's not correct is because you're sort of condensing the number of substituents you can have in the overall name. So you want the longest name possible, which reduces sort of the carbon count in the substituents. Does that make sense? So each of these 6-ethyl, 3,5-dimethyl 4-propyl, that's the shortest chain they can be attached to that longest chain. That's further emphasized in choices C and D, where in both cases a shorter chain has been chosen. And then here you'll notice you have this really long propyl chain. And then here in D, you have a really long 1, 2, 3, 4, 5, 6 carbon chain. So that's way too long of a substituent to be correct in terms of how the nomenclature rules read. So really look for the longest chain, and from there, you're on the right path. The other thing I want to emphasize is you can number the chain sort of front two ways, forward and backwards. So for example, 1, 2, 3, 4, 5, 6, 7, 8, 9. Or in blue, the reverse. If you add up the sum of these numbers, 6 plus 3 plus 5 plus 4, that's going to help you determine which way to properly number the chain. The sum of all of those numbers has to be the smallest possible sum it can be. If you use the numbers in blue, I guarantee you it's going to be greater than the numbers in red. Is that clear? No? So what do we have? 14. So was that 18, 6 plus 3 plus 5 plus 4. Now let's do that in blue. That would be 3 plus 4 plus 5 plus 6. What does that get? 18? Well, don't I look like a horse's patoot? So that if you come into that scenario, what you'll find is that if you go back to the alphabetical argument of the rule, the numbers in red place those substituents properly on the chain. But overall, if it comes down to this argument, it has to be the lower of the two numbers. Questions? So we'll do two more like this. I think these are the same, maybe not. So these are 4 different molecules asking you to find which one is 4-ethyl 2,3-dimethyl octane. Now keep in mind, when you're looking at each individual one, you might have to walk different paths to find the longest carbon chain. So that's probably where you're going to put the most time and effort into. And really the way you solve these, you read the name from left to right. But like when you're drawing the structure or figuring out which one is the correct answer, you sort of have to work from right to left. So you want to find that first. What's the longest chain? Then you number it, forward and backwards both ways. See if it has the right substituents at those locant numbers. What do you think the answer is? B, if you're scanning the slide, it's written up there. So it's B. Let me highlight in green that would be the longest chain. Now if we number that, so 8, that gives us the octane. We look at positions 2 and 3, we have the methyl groups. Maybe I'll get fancy with the colors here. So there's the octane. In blue, there's the methyls. And then in yellow, there's the ethyl. So what is that? 6 plus 3, 9. If you number it the other way, you'll see in this case that numbering would be wrong. So that would give us 5 plus 6 plus 7. Was that 18? So there's an example where you sort of apply that test of the rule to figure out which one is correct in how you number the chain. All this. I think these are the same problems, but now we're asking which one is 5-ethyl 3,4-dimethyl-nonane. So we'll highlight the longest chain in green, write the numbers in, and then make sure that the substituents are on those locations. So what do you think the answer is? So D, I had to give myself a clue. I wrote it on the slide. So visually, sometimes you can see, okay, that looks like the longest path, but again, if not, you have to walk, what I mean, walk these different paths, count it. So you'll have to put some work in that way, figuring that out. So we'll write the correct way in red here, 1, 2, 3, 4. So there's the 3,4 dimethyl, 5-ethyl, 6, 7, 8, 9. So the methyl's in blue here, and then the ethyl in yellow. So again, this is sort of a theoretical exercise in the sense that, most of the molecules we look at aren't going to be this big. They're going to have other functional groups, and as we get to those functional groups, then we're going to add a layer to the nomenclature. So like when we get to alcohols, they're named a little bit different, but these fundamental rules still hold. So in the prior couple questions, all of the substituents that were coming off the chain were linear, meaning that there was no branching of the substituent. If there is a branched substituent, these common names are still used. And when you're putting them in order of the name, you sort of ignore these prefixes that I'm going to talk about. So if you have a 3-carbon substituent, so normally if it was attached there, that would be the 1 position, and it would be propyl. But since it's bonded to the 2 position, it's called isopropyl. Iso just means same. That comes from you have 2 methyl groups. So we use that iso, and that's abbreviated italicized I. When you're sticking it in the name, again, in terms of the alphabet, you follow the P for propyl, not the I for iso. If you have a 4-carbon unit that's branched with 2 of the same methyl groups, this is called isobutyl. So notice kind of the similarity there. There's a 3-carbon chain. It's branched at the 2 position and has this extra methylene group. Since it's 4 carbons, it's a butyl derivative. It's called isobutyl. A 4-carbon substituent that's linear but bonded to the 2 position is called secondary butyl or sec-butyl. So again, these would be B in the order of how they're listed in the name. The third example of a 4-carbon unit is called tertiary or tert-butyl. So again, it's the longest chain there is is 3 carbons. Then you have this methyl group at the 2 position. So that's called tert-butyl. And then a 5-carbon unit that has a tert-butyl group plus a methylene is called neopentyl. I don't know what neo means other than Keanu Reeves in The Matrix, but it is what it is. And again, as I said, these prefixes iso, sec, tert, and neo are not considered part of the name for the alphabet. Just the sort of carbon substituent chain. And so here's some examples of that, where you find the longest chain, and then the substituents coming off that chain are branched. So we'll do the leftmost one first. And hopefully you can see visually that the longest chain, as it's highlighted in green, is that. And then secondarily, we would want to start numbering from the right-hand side. Just visually, it looks like the substituent is closer to that terminal carbon than on the left. Say 1, 2, 3, 4. So the substituents on carbon 4. So 8 carbons. This is an octane derivative. And then at carbon 4, we have an isopropyl group. So we would say 4 isopropyl octane. So the nomenclature rules, I think were developed in like the 1930s or 40s or whatever. And really what's nice about them is no matter how complex a molecule is, like the rules always work and you can name something. For this class, again, things will be relatively straightforward. I use a computer program that algorithms have been designed that can name anything. So it's something you have to go through, call it hazing or whatever, but nowadays you just draw it in a program and it names it for you. If you're ever unsure, on the exams and whatnot, you can go to PubChem or Sigma Aldrich. You type in a molecular formula, it's going to spit out names of things for you. But you sort of need to understand the fundamentals of how it works. So here's the rightmost structure, and it's asking you to figure out what the name of that is. So I would say the first question is how many carbons are in the longest chain? 7, so it's going to be a heptane derivative. So we'll eliminate D. If you look, you see at this position here, like when it branches off, they're both 2 carbons. So 2 carbons, then you get to this one. So it doesn't matter which path you take there, you're still going to get to 7. So we'll just do it in a linear path in green here. So there's 2, 3, 4, 5, 6, 7. And now we would want to start numbering this from the left-hand side, because as we walk along the path, we're going to hit the first substituent quickest, meaning it's going to get the lowest locant number. So at position 3, we have a 2-carbon unit, so that would be ethyl. Then position 4, it's a 4-carbon unit that's branched, and that's called tert-butyl. So again, in terms of alphabetizing them, the B comes before the E, so we end up with 4-tert-butyl, 3-ethyl heptane. Choice A is if you numbered the longest chain going from right to left. So again, to demonstrate that, 4 plus 3 equals 7. If you did it the other way, 4 plus 5 equals 9. Yeah, so the correct answer is B. And so I numbered the chain in red. And so just sort of visually looking at it, as I'm walking along this chain, I can see that when I get to carbon 3, I'm going to hit that first substituent. If I number it in blue, if I were to walk the other way, I have to get to carbon 4 before I hit the first substituent. And then that's going to make the locations 4 and 5. So that sum is 9. When I'm going in red, it's 3 and 4. That sum is 7. So in terms of these numbers, that sum has to be the lowest possible sum it can be, just as part of the logic of the rules. And so there are those 3 compounds. You can see the one in the middle, the branch substituent is secondary butyl.
Why is it that 4-tert-butyl goes before 3-ethyl or heptane?
So again, the order is alphabetical. Okay. And then again, when you have these like prefixes for the branched ones, that T or I or S, that doesn't count. So even though you're showing 4 before 3, the way the rules are written, it's alphabetical according to the substituent.
Okay.
Yeah.
On the last slide, you did I'm just confused, you did some addition, one was 7 and one was...
Any questions on the sort of general nomenclature rules for linear and branched alkanes? Yeah.
So on the last slide.
So we'll spend a brief 3 to 5 minutes on cyclic nomenclature. Again, we're not going to get terribly fancy with these, with their like a million substituents coming off. Basically, what you do when there's a ring or a cyclic structure is you count the total number of carbons in the ring. You find the alkane name and you stick cyclo in front of it. So a 3-membered ring is called cyclopropane. 4 is cyclobutane. And then you can see as you increase the carbon count. So you can hang substituents off those rings, and it's the same rules apply. You'd number the ring both ways, see what substituents are hanging off what carbons, and then give them alphabetical priority, and then the numbers have to add up to the lowest sum they can be. So here is just another sort of practice slide you can work on where you're given the molecular formula for a cycloalkane. Again, these have 1 degree of unsaturation due to the ring. And for C4H8, what I mean by N ring, so that would be cyclobutane, the largest ring possible. And then N-1 ring would be now cyclopropane, and then you have a 1 carbon substituent. So you have your triangle, you shove a methyl group on there, and that would be called methyl cyclopropane. And then you can see the numbers for 5 and 6. Just practice drawing the different ring sizes, put the substituents on. For example, when you get to C6H12, so this is a 6-membered, a 4-membered ring. For that molecular formula can have 7 constitutional isomers. So that's quite a bit. See if you can draw them all and name them all, and that's good practice for nomenclature. So the last slide here is really more informational than anything else. I don't expect you to sort of do this from memory because it does increase in complexity, but I want to show it to you because sometimes we'll see these things and they definitely do exist. You can have compounds that have multiple rings, and the way that the rings are attached to one another are classified in 2 ways. The first is called bicyclic, and the second is called spirocyclic. So let's look at this first one here. It's called bicyclo-1,1,0-butane. And maybe take 15, 20 seconds to think about the name in relation to the structure that's shown and see if you can make sense of how that name relates to the structure. So I'll explain it again from the name, going sort of backwards, right to left. So it says butane. That means 4, right? So there's 4 total carbons. 1, 2, 3, 4. They all have bicyclo in front of them. And then what does this stuff in the square bracket mean? The 3 numbers in the square bracket are what we say the bridge between the 2 rings. And so here and there, that's the bridge. The 1 and the 1 refer to the number of carbons that are in each ring. So you have 1 and 1. The 0 means there's no carbons along the bridge. So the next one, bicyclo-2,1,1-hexane. So 1, 2, 3, 4, 5, 6 total carbons. The bicyclos in front. The 2,1,1, these numbers will always go in order of decreasing number. So you have 2 carbons. So there's the bridge there and there. You have 2 carbons, 1 and 1. And so these things do exist. People study them. As we'll learn a little bit later in this module, the reason people study them is, if you look, you have a triangle here, an sp3 hybridized carbon. The bond angle is significantly constrained. So it's not its normal 109.5. It's a lot lower than that. And what that means is there's a lot of energy in that bond angle. And so that energy wants to be released. And so people study these as high energy materials. You'd call it a bomb, but it's basically, it wants to get rid of that energy somehow. And so it's high energy. So the other class is called spirocyclic. And so let's look at this nomenclature. Spiro is before the square bracket. How many carbons do we have here? 1, 2, 3, 4, 5. So that matches what we see in the total carbon count. And then look at these numbers here. There's only reporting 2 of them. So 1, 2, 1, 2. The last carbon is the one that bridges the 2 rings in the spiro junction. So by necessity, that carbon is always quaternary. It has no hydrogens bonded to it. Any nomenclature questions before we yoink the wheel and make a hard right here? So the next part of this module is on conformational analysis. And so even though when I draw something on the slide, you draw it on your tablet or paper, you're drawing like a static image. How many of you know what like a Polaroid camera is? When I was young, you take a picture and it printed it out. That's like a snapshot in time, right? And so what you're drawing on your paper is a snapshot. So molecules are always moving. There's always energy associated with them. Even at absolute zero, where there's no heat, there's something called 0 point energy. And so energy takes many different forms. And what we're going to study in this part of the module is rotational energy. We know that bonds have movement from IR, they're stretching. And so what we're going to look at in this part of the module is not stretching so much, but rotation. And so that's going to limit us to sigma bonds specifically. So to give you an example of this, sort of what I mean by that static picture of a molecule. The easiest thing to consider first is butane. So we know butane is a 4-carbon alkane. So I've drawn it one way. But I can also draw it another way. So those are both butane. It's the same molecular formula, but the difference between them is these are called conformational isomers. or just abbreviated conformers. And those conformers have different energies associated with them. And so what that means is one of those conformers will exist in a higher population at room temperature than the other. And so we want to understand why that is, and using the model is really going to help us visualize that. So again, molecules are dynamic. They're always moving. There's always energy associated with them. We want to really cement in our minds that every sigma bond in a molecule is going to rotate, and that's going to lead to different conformers. So in 1969, the Nobel Prize in Chemistry was awarded to Barton and Hassel for their contributions in the development of conformation as it relates to chemistry. So this ultimately ties back really into steroids. Back in the early 1900s, through the 30s and 40s, people were interested in the actual structure of steroids, like cholesterol, estrogen, testosterone, and they basically figured out that sort of the way you draw something flat on paper is not how it looks in real life, because we know that due to hybridization in geometries, these things are 3D, and that in 3D the relationships are not always in the same plane. They can be in different planes, and that's what conformational analysis is all about. If you recall from Module 2 when we talked about coupling constants, remember that angle changes, that changes the Hertz value of the coupling. We drew this thing called a Newman projection. So Newman was a professor at Ohio State. We need a building after him. He was a carbohydrate chemist. So he came up with this way of looking at these molecules to help understand conformational analysis. So imagine I'm holding methane. So the yellows are your hydrogens. The red and purple, blue, these are also hydrogens, but when we go to propane, they're going to be different things. So instead of looking at the molecule sort of in the longest chain like we're used to looking at it, we're going to change our viewpoint now where we're looking down the carbon-carbon axis. So the front carbon, you see those three substituents, so 1, 2, 3, that's these lines. The back carbon is represented by a circle or a ball. And then notice the three lines coming out of that originate from the circle. That means, okay, there's the carbon itself, and then these substituents are coming out of it. So you place the front on top of the rear, and that gives you the Newman projection. And so we know that carbon has 4 substituents. So you see the 3 on the front, you see the 3 on the rear. The fourth one is that bond. So remember, when you do that rotation, you're looking down that sigma bond. And I'll show more of this on the next slide, but briefly while I'm holding this. This carbon is sp3 hybridized, so the HCH, that bond angle is 109.5. So you have 3 points that make an angle, but now again what we're going to talk about, say in relation of like this blue hydrogen to this red one, I colored them so that we can see things are changing. The new type of angle we're going to talk about is a dihedral angle. So that's the relationship of the front substituent to the back substituent. So overall, you're going from that carbon to this angle. It's not a bond angle, it's a dihedral angle. And so you can see as I rotate this, notice, I think I have the red in the front on the other slides. Notice how I'm going to keep the back carbon the same, but I'm going to move the front one. So notice the angle is changing. And so it's not terribly impressive if they're both hydrogen, but when they become other substituents, we want to see how that rotation affects what conformer exists in the highest percentage. So again, here is ethane. You have two methyl groups bonded together. So both of these are CH3 groups. And we're going to stick the red H up, the blue H down. And I believe what I'm doing is rotating the front carbon. So when you're looking down this conformation is called staggered. And I'm going to rotate this way. And now pretend that you can't see the back substituents. I mean, you can, but that's called eclipse. So when you're doing this, you're either in staggered or eclipsed form. And you know what is not apparent with the ball and stick model. Again, these carbons take up space, right? So they're pretty big. The hydrogens are smaller, but as this moves, imagine these hydrogens are close to one another. And really what they want to do is repel. So as it's eclipsing, it's repelling. That's distorting the bond angle, and that requires energy. And so that's what's listed there. It says plus 4 kilojoules per mole once it goes from staggered to eclipsed. So since there's 3 of them, the total energy for that eclipsed conformer is 12 kilojoules per mole. And so you just go round and round. I mean, don't think that it's spinning as slow as I mean, this happens like trillions of times per second. It's really fast, right? But every time it does that, the eclipsed is now higher energy. And so again, that's going to relate to reactivity when we start drawing out these higher order alkanes. So ethane has 2 conformers, staggered and eclipsed. And so you don't have to memorize it. I mean, it's there. You'll be given it on the exam. But if you want to develop an intuition, the energy penalties are listed here in this little menu. Every HH eclipsing is 4 kilojoules per mole. If you have a hydrogen eclipsing a methyl, that's 6. Let's skip this one, see how the word's different. If you have 2 methyls eclipsing, that's the highest, it's 11. What does the word gauche mean? Gauche is a penalty that doesn't happen in an eclipsed conformation. It happens in a staggered. So notice it says methyl, methyl. So if this was methyl and this was methyl, they have to be right next to each other. So that's called gauche, and I'll explain that hopefully in the next 10 minutes, but if not, in the next lecture. So gauche is only present in staggered conformations. So we did this one. The eclipsed for ethane is 4 kilojoules per mole times 3. That gets us our 12. This is a blank slide of basically how we're going to start looking at these things. On the x-axis is the dihedral angle. The y-axis is the relative energy. So we're just considering eclipsed, gauche. We're not considering the absolute energy of the molecule, just as we do the rotations. Then up here in these boxes, we'll draw the conformers, and then we'll plot what their energy is and connect the dots. So what happens if you look at ethane to the top left and you track that red hydrogen, really it's only achieving the 2 conformers. The staggered, we're going to say that has 0 energy penalty associated with it. So that's the 0 over here on the y-axis. Then as we start rotating it, it gets eclipsed. So now all the hydrogens are eclipsed to one another, so that's 12. It does a further rotation, it goes back down to 0. So this pattern just repeats for infinity. Now, every molecule is not that simple and it's not going to look like that. So the graph will change as you start. Basically what we're going to do is substitute an H, go to propane, substitute 2 H's, go to butane, look down different bonds, do the rotations, and calculate the energies. I want to say as well, again, really notice that these things don't jump from 0 to 12. You know, it does follow a path. And we'll look at more of these type of diagrams as we learn reactions. These are called reaction coordinates. As a reaction proceeds, how much energy is put in, given off, and then we sort of plot it in that Polaroid sense where it's just a slice of time. Any questions at this point? Yeah. Yeah, you're adding all the eclipsing interactions. So we'll go through definitely propane. If there's enough time, we'll do butane today. So notice the prompt. It says propane along the C1 to C2 bond. When you're converting that into a Newman projection, that matters because it's telling you what's the front carbon, what's the back carbon. So just pay attention to that so you're looking down the right sigma bond, and then you can get your conformers correct. So let's just do that on this slide, then we'll go to that plot on the next slide. So here's propane. And here's the standard organic chemistry eyeball. Your eyeball is in the plane of the whiteboard, and you're looking down C1 to C2. And so hopefully you can follow how I'm going to draw this. I mean, I'll explain it, but let me just draw some stuff first. I'm going to switch over to black here. So that's the front carbon. If that's your eyeball, what should go up here? Huh? A hydrogen, but what color hydrogen? The red hydrogen. So I don't have this color coded, but this hydrogen here, that's indicated with the wedge that's coming out towards you. That's going to go on the right. And then the hydrogen with the dash is going to go on the left. Now keep in mind, they're all hydrogens, so you can just stick them in there. But if they're other substituent, that's eventually going to matter. So let's put in, there's the back carbon. So now looking down 1 to 2, where does the blue methyl group go? On the bottom. And then your last 2 hydrogens. So let me just point out again. You need 4 atoms to make up a dihedral angle. And really a dihedral angle is the intersection of 2 planes. So for example, if we're doing that red H to that blue carbon, so we're going to determine the dihedral angle between HCCC. And again, so there's sort of your first set of 3, and then your second set of 3 as they intersect. Do you all have those plastic model kits? You taken the wrapper off them yet and used them? So this is a good opportunity to start building. This is the same type kind of, it's just the lecture model, but I definitely encourage you to use them for this to help you understand what's going on. But let's go ahead and we'll redraw that. So I'm gonna keep the back carbon locked, and I'm just gonna rotate the front one, and we do this in 60-degree increments, and so that staggered is now going to become eclipsed. And so the question is asking you, what's the energy penalty for that eclipsed conformation? So we have HH, we go over to the energy menu here, that's +4. HH is +4, and now we have a new one, methyl H, that's +6. So that gets us +14 kilojoules per mole. So you can see of propane, there's really, again, only two. You have the staggered, then the eclipsed. We're a little bit out of time, but we'll start again on Wednesday with butane. In the meantime, try to do this same thing with butane, but look down C2 to C3. You'll see that the graph looks different.